Hello, and welcome back to the channel. Today's crucial topic is failover and redundancy, building for when things break. In the real world of computing, failures are not exceptions. They are inevitable. Whether it's a power outage, a hardware crash, a subtle software bug, or even simple human error, systems will eventually break. Failover and redundancy are the foundational principles that ensure a single point of failure doesn't cascade into a total system collapse. In today's digital landscape, users expect near-perfect uptime, often aiming for 5 nines, 99.999% availability. Without meticulous planning for failover and redundancy, you're essentially gambling with your system's reliability, leading to unhappy users and lost business. Giants like Amazon, Netflix, and Google have layers upon layers of these mechanisms baked into every part of their infrastructure. Our ultimate goal today is to understand how to design for resilience, achieve high availability, and provide an uninterrupted user experience, even in the face of inevitable failures. At its core, failover is the automatic switching of operations from a primary, failed component to a healthy, standby system. This transition happens seamlessly, often without human intervention, to maintain service availability. Failover mechanisms can be implemented at virtually any layer of your system architecture, from individual application servers and databases to load balancers, network devices, and even entire data centers. The execution of a failover can take different forms. Active-passive or cold/warm standby in this setup, a primary component actively handles traffic, while a secondary, standby component is idle or minimally active. It only becomes active and takes over traffic once the primary is detected to have failed. This is simpler to manage, but can have a brief downtime during the switch. Active-active or hot standby here, both or all, components are actively processing traffic simultaneously. If one component fails, the remaining active components simply pick up the slack. This offers higher availability and often zero perceived downtime, but is more complex to implement, particularly regarding data consistency. A common example is a database setup. If a primary database server fails, traffic is automatically redirected to a secondary replica that is promoted to become the new primary, ensuring continuous data access. The goal of failover is to provide zero or minimal downtime during disruptions. While failover describes the action of switching, redundancy is the underlying principle that makes failover possible. Redundancy means having backup components or duplicate resources ready to take over in case of a primary system's failure. It's the strategy of building in spare parts. Redundancy manifests in several forms. Hardware redundancy. This involves duplicating physical components, such as having multiple servers, redundant power supplies, multiple network interface cards, or even diverse network paths to a data center. Software redundancy. This is achieved by running multiple instances of your application code, perhaps as multiple identical servers, containers, or microservices across different machines. If one software instance crashes, others are still available to handle requests. Data redundancy. This is crucial for data integrity and availability. It involves creating and maintaining copies of your data across different storage devices, machines, availability zones, or even geographical regions. This ensures that even if one copy is lost, others remain. The core idea behind redundancy is simple. Don't rely on one of anything. It's like having multiple engines in an airplane. One failure doesn't mean the entire system collapses. There are always backups. Failover can be implemented at various layers of your architecture, each addressing specific types of failures. DNS failover. This is one of the highest level failover mechanisms. When a primary server or data center fails, a DNS service like Cloudflare or AWS Route 53 detects the outage through health checks. It then automatically updates the DNS records to point traffic to a healthy, redundant IP address, example, in a different data center. The downside is the time it takes for DNS changes to propagate globally, DNS propagation delay. Load balancer failover. Load balancers, as we've discussed, are designed to detect failed backend instances. If a server in their pool becomes unhealthy, the load balancer automatically stops sending traffic to it and reroutes all requests to the remaining healthy instances. This provides granular, instance-level failover. Database failover. This is critical for data persistence. It typically involves replica promotion, where a read-only replica is promoted to become the new primary for writes, or a leader election process among a cluster of database nodes, example, using tools like Patroni with PostgreSQL. This ensures continuous database operations even if the primary database server goes down. Service mesh failover. In microservices architectures, a service mesh like Istio or Linkerd can provide sophisticated failover capabilities at the service-to-service communication layer. This includes automatic retries for failed requests, intelligent rerouting to healthy instances of a service, and circuit breaking to prevent cascading failures. All these mechanisms rely on continuous health checks and heartbeat signals to quickly detect failures and trigger the failover process. To build truly resilient systems, redundancy must extend beyond individual machines to geographical distribution. Availability zones. AZ's cloud providers like AWS, Azure, GCP divide their regions into multiple, isolated availability zones. Each AZ is a physically distinct data center with independent power, cooling, and networking. Deploying your application components, servers, databases, queues, across multiple AZs provides higher fault isolation. If one AZ experiences an outage, example, a power failure, your application continues to run in other AZs within the same region. Multi-region architecture. For the highest level of resilience and disaster recovery, organizations deploy their applications across multiple geographically distinct regions. This protects against catastrophic failures that might affect an entire region, example, a major natural disaster. While more expensive and complex to manage consistency across regions, it ensures near-continuous operation even in extreme scenarios. The synergy of load balancing, distributing traffic, auto-scaling, dynamically adjusting capacity, and redundancy across AZs and regions is what creates truly bulletproof availability. The design choice here always involves a crucial balance between the cost of maintaining this redundancy, the acceptable latency for users, and the desired level of reliability. While vital, implementing robust redundancy and failover is fraught with challenges. Split-brain scenarios. This is a notorious problem in distributed systems. It occurs during a network partition when two or more nodes incorrectly believe they are the designated leader, or primary because they've lost communication with the true leader. This can lead to conflicting writes and data corruption. Robust consensus algorithms are needed to prevent this. Failback planning. The process of switching traffic back to the original primary systems once they have recovered from a failure is often more complex and riskier than the initial failover. It requires careful coordination, data synchronization, and validation to avoid new outages. Overhead cost. Maintaining redundancy is inherently expensive. You're effectively paying for duplicate hardware, software licenses, network bandwidth, and operational overhead, which significantly increases infrastructure costs. This must be balanced against the cost of downtime. Stale replicas. In asynchronous replication models, replicas can fall behind the primary, leading to stale data. Ensuring data consistency across replicas during and after failovers, particularly with the risk of data loss on primary failure, is a critical challenge. Testing failover is often skipped. This is a major pitfall. Many organizations build elaborate failover mechanisms, but rarely test them under realistic conditions. It's often during an actual outage that flaws in the failover logic are discovered. Regular failure drills and chaos engineering are the real difference makers here. Let's look at some prime examples of redundancy and failover in action. Netflix Chaos Monkey. This famous tool from Netflix is part of their simian army. It's designed to randomly disable or kill services and instances in their production environment. The purpose is not to cause outages, but to proactively test the resilience and failover readiness of their systems under constant pressure, forcing engineers to build in robust recovery mechanisms. Google Spanner. As previously mentioned, Google Spanner is a globally distributed database that achieves high availability and strong consistency across continents. It inherently incorporates multi-zone and multi-region replication with automatic failover and leader election, making it incredibly resilient to node or even data center failures. Banking systems. Financial institutions operate with some of the highest availability requirements. Their systems are designed with no single point of failure, SPUF, employing active data centers, redundant networking, and robust failover procedures to ensure continuous transaction processing, as even minutes of downtime can translate to massive financial losses and loss of trust. The key lesson from these examples is clear. Truly resilient systems don't just react to failure. They proactively plan for it, design for it, and constantly test their ability to recover. To summarize our deep dive into failover and redundancy. When discussing system design, common interview prompts often revolve around questions like, how would your design handle a server crash? Or, what happens if an entire region goes offline? Your ability to articulate a clear strategy for these scenarios is crucial. Always be prepared to highlight failover paths, how traffic shifts, fallback strategies, what happens if the primary failover also fails, and robust backup plans for data recovery. In a production environment, the true test of your resilience planning comes from running failure drills. Don't wait for a real outage. Proactively inject failures and test your system's recovery mechanisms. Test your system before your users do. Finally, remember this critical mantra: no failover equals a ticking time bomb. Robust failover and redundancy are not luxuries. They are fundamental requirements for building reliable, scalable systems in today's demanding digital world. Before you go, I'd love to hear from you in the comments. If you found this video helpful, do give it a like, share it with your friends, and of course don't forget to subscribe to the channel to help us grow. I will see you in the next one. Till then, happy learning.